This is Concepts of Programming Languages by Robert W. Sebesta, Chapter 15, Functional Programming Languages. This chapter introduces functional programming as some of the programming languages that have been designed for this approach to software development. We begin by reviewing the fundamental ideas of mathematical functions, because functional languages are based on them. Next, the idea of a functional programming language is introduced, followed by a look at the first functional language, Lisp. The next, somewhat lengthy section is devoted to an introduction to Scheme, including some of its primitive functions, special forms, functional forms, and some examples of simple functions written in Scheme. Next, we provide brief introduction to Common Lisp, ML, Haskell, and F#. Then we discuss the support for functional programming that is included in some imperative languages. The following section describes some of the applications of functional programming languages. Finally, we present a brief comparison of functional and imperative languages. 15.1 Introduction. Most of the earlier chapters in this book have been concerned primarily with the imperative programming languages. The high degree of similarity among the imperative languages arises in part from one of the common bases of their design, the von Neumann architecture, as discussed in Chapter 1. Imperative languages can be thought of collectively as a progression of development to improve the basic model, which was Fortran 1. All have been designed to make efficient use of von Neumann architecture computers. Although the imperative style of programming has been found acceptable by most programmers, its heavy reliance on the underlying architecture is thought by some to be an unnecessary restriction on the alternative approaches to software development. Other bases for language design exist, some of them oriented more to particular programming paradigms, or methodologies that to efficient execution on a particular computer architecture. Thus far, however, only a relatively small minority of programs have been written in non-imperative languages. The functional programming paradigm, which is based on mathematical functions, is the design basis of the most important non-imperative styles of language. This style of programming is supported by functional programming languages. The 1977 ACM Turing Award was given to John Backus for his work in the development of Fortran. Each recipient of this award presents a lecture when the award is formally given, and the lecture is subsequently published in the communications of the ACM. In his Turing Award lecture, Backus 1978 made a case that purely functional programming languages are better than imperative languages because they result in programs that are most readable, more reliable, and more likely to be correct. The crux of this argument was that purely functional programs are easier to understand both during and after development, largely because the meanings of expressions are independent in their context. One characterizing feature of a pure functional programming language is that neither expressions nor functions have side effects. In this lecture, Backus proposed that a pure functional language, FP or functional programming, which he used the frame of his argument. Although the language did not succeed, at least in terms of achieving widespread use, his idea motivated debate and research on pure functional programming languages. The point here is that some well-known computer scientists have attempted to promote the concept that functional programming languages are superior to the traditional imperative languages. Though those efforts have obviously fallen short on their goals, however, over the last decade, prompted in part by the maturing of the type functional language such as ML, Haskell, or OCaml, and F#, there has been an increase in the interest in and use of functional programming languages. One of the fundamental characteristics of programs written in imperative languages is that they have stated which changes throughout the execution process. This state is represented by the program's variables. The author and all the readers of the program must understand the uses of its variables and how the program's state change through execution. For a large program, this is a daunting task. This is one problem with programs written in an imperative language that is not present in a program written in a pure functional language. For such programs, have neither variables nor state. Lisp began as a pure functional language, but soon acquired some important imperative features that increased its execution efficiency. It is still the most important of the functional languages, at least in the sense that it is the only one that has achieved widespread use. It dominates in the areas of knowledge representation, machine learning, intelligent training systems, and the modeling of speech. Common Lisp is an anagram of several years early 1980s dialects of Lisp. Scheme is a small, static scope dialect of Lisp. Scheme has been widely used to teach functional programming. It is also used in some universities to teach introductory programming courses. The development of the type functional programming language, primarily ML, Haskell, OCaml, and F# has led to a significant expansion of the areas of computing in which functional languages are now used. As these languages have matured, their practical use is growing. They are now being used in areas such as database processing, financial modeling, statistical analysis, and bioinformatics. One objective of this chapter is to provide an introduction to functional programming using the core of Scheme, intentionally leaving out its imperative features. Sufficient material of Scheme is included to allow the reader to write some simple but interesting programs. It is difficult to acquire an actual feel for functional programming without some actual programming experience, so that it is strongly encouraged. 15.2 Mathematical Functions. A mathematical function is a mapping of members of one set called the domain set to another set called the range set. A function definition specifies the domain range sets either explicitly or implicitly along with the mapping. The mapping is described by an expression or, in some cases, by a table. Functions are often applied to a particular element of the domain set, given as a parameter to the function. Note that the domain set may be the cross product of several sets, reflecting that there can be more than one parameter. A function yields an element of the range set. One of the fundamental characteristics of mathematical functions is that the evaluation order of their mapping expressions is controlled by recursion and conditional expressions, rather than by the sequencing and iterative repetition that are common to programs in the imperative programming languages. Another significant and important characteristic of mathematical functions is that because they have no side effects and cannot depend on any external values, they always map a particular element of the domain to the same element of the range. However, a subprogram and an imperative language may depend on the current values of several non-local or global variables. This makes it difficult to determine statically what values of the subprogram will produce and what side effects it will have on a particular execution. In mathematics, there is no such thing as a variable that models a memory location. Local variables in functions in imperative programming languages maintain the state of the function. Computation is accomplished by evaluating expressions in assignment statements that change the state of the program. In mathematics, there is no concept of the state of a function. A mathematical function maps its parameters to a value or values, rather than specifying a sequence of operations on values in memory to produce a value. 15.2.1 Simple Functions. Function definitions are often written as a function name, followed by a list of parameters or parentheses, followed by mapping expressions. For example, cube, open parentheses, x, close parentheses, is equivalent to x times x times x, where x is a real number. In this definition, the domain and range sets are the real numbers. The symbol equivalent is used to mean is defined as the parameter x can represent any number of the domain set, but it fits to represent one specific element during evaluation of the function expression. This is one way the parameters of mathematical functions differ from the variables in imperative languages. Function applications that are specified by pairing the function name with a particular element of the domain set. The range element is obtained by evaluating the function mapping expression with the domain element substituted for the current of the parameter. Once again, it is important to note that during evaluation, the mapping of a function contains no unbound parameters, where a bound parameter is a name of a particular value. Every occurrence of a parameter is bound to a value from the domain set and is a constant during evaluation. For example, consider the following evaluation of cube x. Cube 2.0 is equal to 2.0 times 2.0 times 2.0, which equals to 8. The parameter x is bound to 2.0 during the evaluation and there are no unbound parameters. Furthermore, x is a constant. Its value cannot be changed during the evaluation. Early theoretical work on functions separated the task for defining a function from that of naming the function. Lambda notation, as devised by Alonso Church in 1941, provides a method for defining nameless functions. A lambda expression specifies the parameters and the mapping of a function. The lambda expression is the function itself, which is nameless. For example, consider the following lambda expression. Lambda, open parentheses, x, close parentheses, x times x times x times x. Church defined a formal computation model, a formal system for function definition, function application, and recursion. Using lambda expressions, this is called Lambda Calculus. Lambda Calculus can either be tabbed or untabbed. Untabbed Lambda Calculus serves as the inspiration for the functional programming languages. As stated earlier, before evaluation, a parameter represents any member of the domain set, but during evaluation it is bound to a particular member. When a lambda expression is evaluated for a given parameter, the expression is said to be applied to that parameter. The mechanics of such an application are the name as for any function evaluation. Application of the example lambda expression is denoted as in the following example. Open parentheses, lambda, open parentheses, x, close parentheses, x times x times x, close parentheses, open parentheses, 2, close parentheses, which result in the value 8. Lambda expressions, like other function definitions, can have more than one parameter. 15.2.2 Functional forms. A higher order function or functional form is one of the either that takes one or more functions as parameters or yields a function as it results on both. One common kind of functional form is function composition, which has two functional parameters and yields a function whose value is the first actual parameter function applied to the result of the second. Function composition is written as an expression using O to the power as an operator, as in H is equivalent to F power of O and G. For example, if f x is equivalent to x plus 2 and gx is equivalent to 3 times x. That is defined as hx is equivalent to f gx or hx is equivalent to 3 times x plus 2. Applied to all is a functional form that takes a single function as parameter. If applied to a list of parameters, applied to all applies its functional parameter to each of the values in the list parameter and collects the result of a list or sequence. Applied to all is denoted by alpha. Consider the following example. In programming languages, they are often called map functions. Let hx be equivalent to x times x. Then alpha, open parentheses, h, comma, open parentheses, 2, 3, 4, close parentheses, yields, open parentheses, 4, 9, 16, close parentheses. There are functional forms, but these two examples illustrate the basic characteristics of all of them. Section 15.3 Fundamentals of Functional Programming Languages. The objective of the design of a functional programming language is to mimic mathematical functions to the greatest extent possible. This results in an approach to problem solving that is fundamentally different from approaches used by imperative languages. With an interactive language, an expression is evaluated as the result is stored in a memory location, which is represented as a variable in program. This is the purpose of assignment statement. This necessary attention to memory cells, whose values represent the state of a program, results in a relatively low-level programming methodology. A program in an assembly language often must also store the results of a partial evaluations of expressions. For example, to evaluate open parentheses x plus y, close parentheses, over open parentheses a minus b, close parentheses. The value of open parentheses x plus y, close parentheses, is computed first. That value must then be stored while open parentheses a minus b is evaluated. Close parentheses before that. A minus b, close parentheses, okay? The compiler handles the storage of intermediate results of expression evaluations in high-level languages. The storage of intermediate results is still required, but the details are hidden from the programmer. A purely functional programming language does not use variables or assignment statements, thus freeing the programmer from concerns related to the memory cells or state of the program. Without variables, iterative constructs are not possible, for they are controlled by variables. Repetition must be specified with recursion rather than with iteration. Programs are function definitions and function application. Specifications and executions consist of evaluating function applications. Without variables, the execution of a purely functional program has no state in the sense of operational and intonational semantics. The execution of a function always produces the same result when given the same parameters. This characteristic is called referential transparency. It makes the semantics of purely functional languages far simpler than the semantics of the imperative languages, open parentheses, and the functional languages that include imperative features, close parentheses. It also makes testing easier because each function can be tested separately without any concerns for its contents. A functional language provides a set of primitive functions, a set of functional forms to construct complex functions from those primitive functions, a function application operation, and some structure or structures for representing data. These structures are used to represent parameters and values computed by functions. If a function language is well designed, it requires only a relatively small number of primitive functions. As we have seen in earlier chapters, the first functional programming language, Lisp, uses a syntactic form for both data and code that is very different from that of the imperative languages. However, many functional languages designed later use syntax for their code that is similar to that of the imperative languages. Although there are few purely functional languages, for example Haskell, most of the languages that are called functional include some imperative features, for example mutable variables and constructs that act as assignment statements. Some concepts and constructs that originated in functional languages, such as lazy evaluation and anonymous subprograms, have now found their way into some languages that are considered imperative. Although early functional languages were often implemented with interpreters, many programs written in functional programming languages are now compiled. Section 15.4. The first functional programming language, Lisp. Many functional programming languages have been developed. The oldest and most widely used is Lisp, open parentheses, or one of its descendants, close parentheses, which was developed by John McCarty at MIT in 1959. Studying functional languages through Lisp is somewhat akin to studying the imperative language through Fortran. Lisp was the first functional language, but although it has steadily evolved for half a century, it no longer represents the latest design concepts for functional languages. In addition to with the exception of the first version, all Lisp dialects include imperative language features, such as imperative style variables, assignment statement, and iteration. Open parentheses, imperative style variables are used to name memory cells whose values can change many times during program execution. Close parentheses. Despite this and their somewhat odd form, the descendants of the original Lisp represent well the fundamental concept of functional programming and therefore worthy of study. 15.4.1 Data types and structures. There were only two categories of data objects in the original Lisp: atoms and lists. List elements are pairs, where the first part of the data of the element, which is a pointer to either an atom or a nested list. The second part of a pair can be a pointer or to an atom, a pointer to another element, or a special value, nil. Elements are linked together in lists with the second part. Atoms and lists are not types in the sense that imperative languages have types. In fact, the original Lisp was a typeless language. Atoms are either symbols in the form of identifiers or numeric literals. Recall from Chapter 2 that Lisp originally used list and its data structure because they were thought to be an essential part of Lisp processing. As it eventually developed, however, Lisp rarely requires the general list operation of insertion and deletion at positions other than the beginning of a list. Lists are specified in Lisp by delimiting their elements with parentheses. The elements of simple lists are restricted to atoms, as in open parentheses A, space B, space C, space D, close parentheses. Nested list structures are also specified by parentheses. For example, the list open parentheses A, open parentheses B, space C, close parentheses, space D, space open parentheses E, space open parentheses F, space G, close parentheses, close parentheses, close parentheses. It's a list of 4 elements. The first is the atom A. The second is the sublist, open parentheses B, space C, close parentheses. The third is the atom D. The fourth is the sublist, open parentheses E, space open parentheses F, space G, close parentheses, which has as its second element the sublist of open parentheses F, space G, close parentheses. In a list implementation, a list is usually stored as linked list structure in which each node has 2 pointers, one to reference the data of the node and the other to form the linked list. A list is referenced by a pointer to its first element. The internal representation for our 2 example lists are shown in figure 15.1. Note that the elements of a list are shown horizontally. The last element of a list has no successor, so its link is nil. Sublists are shown with the same structure. Okay. (15.4.2) The first list interpreter. The original intent of Lisp's design was to have notation for programs that would be as close to Fortran as possible. With additions when necessary, this notation was called M notation, for meta notation. There was to be a compiler that would translate programs written in M notation into semantically equivalent machine code programs for the IBM 704. Early in the development of Lisp, McCarthy wrote a paper to promote Lisp processing as an approach to general symbolic processing. McCarthy believed that Lisp processing could be used to study computability, that at the time was usually studied using Turing machines, which are based on the imperative model of computation. McCarthy thought that the functional processing of symbolic lists was more natural model for computation than Turing machines, that operated on symbols written on tapes, which represented state. One of the common requirements of the study of computation is that one must be able to prove certain computability characteristics of the whole class of whatever model of computation is being used. In the case of the Turing machine model, one can construct a universal Turing machine that can mimic the operations of any other Turing machine. From this concept came the idea of constructing a universal list function that could evaluate any other function in Lisp. The first requirement of universal list function was a notation that allowed functions to be expressed in the same way data was expressed. The parenthesized list notation described in section 15.4.1 had already been adapted to Lisp data, so it was decided to invent conventions for function definitions and function calls that could also be expressed in list notation. Function calls were specified in a prefix list form, originally called Cambridge Polish, as in the following. This name first was used in the early development of Lisp. The name was chosen because Lisp resembled the prefix notation used by the Polish logician Jan Łukasiewicz, and became Lisp was born at MIT in Cambridge, Massachusetts. Some now prefer to call the notation Cambridge prefix. Open parentheses function underscore name parameter 1 C parameter n close parentheses. For example, if plus is a function that takes 2 or more numeric parameters, the following 2 expressions evaluate 12 and 20 respectively. Open parentheses plus 5 space 7 close parentheses return open parentheses plus 3 space 4 space 7 space 6 close parentheses. The lambda notation described in section 15.2.1 was chosen to specify the function definitions. It had to be modified, however, to allow the binding of functions to names so that functions could be referenced by other functions and by themselves. This name binding was specified by a list consisting of the function name and the list containing the lambda expression as in open parentheses function underscore name open parentheses lambda open parentheses param 1 dot 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 param n close parentheses expression close parentheses close parentheses. If you have had no prior exposure to functional programming, it may seem odd to even consider a nameless function. However, nameless functions are sometimes useful for functional programming, open parentheses, as well as in mathematics and imperative programming, close parentheses, period. For example, consider a function whose action is to produce a function for immediate application to parameter list. The produce function has no need for name, so it's applied only at the point of its construction. Such an example is given in section 15.5.14. Lisp functions specified in this new notation were called S-expressions, for symbolic expressions. Eventually, all Lisp structures, both data and code, were called S-expressions. An S-expression can be either a list or an atom. We will usually refer to S-expressions simply as expressions. McCarthy successfully developed a universal function that could evaluate any other function. This function was named eval, and it was itself is the form of an expression. Two of the people in the AI project, which was developed in Lisp, Stephen B. Russell and Daniel J. Edwards, noticed that an implementation of eval could serve as a Lisp interpreter, and they promptly constructed such an implementation. McCarthy et al., 1965. There were several important results in this quick, easy, and unexpected implementation. First, all early Lisp implementations copied eval and were therefore interpretive. Second, the definition of M notation, which was the planned programming notation for Lisp, was never completed or implemented, so S expressions became Lisp's only notation. The use of the same notation for data code has important consequences, one of which will be discussed in section 15.5.14. Third, much of the original language design was effectively frozen, keeping certain odd features in the language such as the conditional expression form and the use of parentheses for both the empty list and logical files. Another feature of early Lisp systems that was apparently accidental was the use of dynamic scoping. Functions were evaluated in the environments of their callers. No one at the time knew much about scoping, and there may have been little thought given to the choice. Dynamic scoping was used for most dialects of Lisp before 1975. Contemporary dialects either use static scoping or allow the programmer to choose between static and dynamic scoping. An interpreter for Lisp can be written in Lisp. Such an interpreter, which is not a large program, describes the operational semantics of Lisp in Lisp. This is vivid in evidence to semantic simplicity of the language. 15.5. An Introduction to Scheme. In this section, we describe the core part of Scheme. Divdic, 2011. We have some chosen Scheme because it is relatively simple, it is popular in colleges and universities, and Scheme interpreters are rarely available, and free also, for a wide variety of computers. The version of Scheme described in this section is Scheme 4. Note that this section covers only a small part of Scheme, and it includes none of Scheme's imperative features. 15.5.1. Origins of Scheme. The Scheme language, which is a dialect of Lisp, was developed at MIT in the mid-1970s. Sussman and Steele, 1975. It is characterized by its small size, its exclusive use of static scoping, and its increment of functions as first-class entities. As first-class entities, Scheme functions can be values of expressions, elements of lists, passed as parameters, and returned from functions. Early versions of Lisp did not provide all of these capabilities. As an essentially typeless small language with simple syntax and semantics, Scheme is well suited to educational applications such as courses in functional programming and also to general introductions to programming. Most of the Scheme code in the following sections would require only minor modifications to be converted to valid Lisp code. 15.5.2. The Scheme Interpreter. A Scheme interpreter in an interactive mode is an infinite read, evaluate, print loop, often abbreviated as REPL. It repeatedly reads an expression typed by the user in the form of a list, interprets the expression, and displays the resulting value. This form of interpreter is also used by Ruby and Python. Expressions are interpreted by the function eval, literal's value, to themselves, so if you type a number to the interpreter, it simply displays the number. Expressions that are calls to primitive functions are evaluated in the following ways. First, each of the parameter expressions is evaluated in no particular order. Then the primitive function is applied to parameter values and the resulting value is displayed. Of course, scheme programs that are stored in files can be loaded and interpreted. Comments in scheme are any text following a semicolon on any line. 15.5.3 Primitive numeric functions. Scheme includes primitive functions for the basic arithmetic operations. These are plus, minus, times, and over for add, subtract, multiply, and divide. Multiply and add can have 0 or more parameters. If multiply is given no parameters, it returns 1. If plus is given no parameters, the returns is 0. Plus adds all of its parameters together. Times multiplies all its parameters together. Divide and subtract can have 2 or more parameters. In this case, subtract all but the first parameter or subtract from the first. Division is similar to subtraction. Some examples are as follows. Expression 42, value 42. Then there is open parentheses, multiply 3, space 7, close parentheses, value 21. Expression, open parentheses, plus 5, space 7, space 8, close parentheses, 20. The next expression is open parentheses, minus 5, space 6, close parentheses, equals to -1. And the next is open parentheses, minus 15, space 7, space 2, close parentheses, 6. The last example, is open parentheses, minus, space 24, space, open parentheses, times 4, space 3, close parentheses, which equals to 12. There are a large number of other numeric functions in scheme. Among them, modulo, round, max, min, log, sin, square root returns the square root of its numeric parameter. If the parameter's value is not negative, if the parameter is negative, square root yields a complex number. In scheme, note that we are uppercase letters for all reserved words and predefined functions. The official definition of the language specifies that there is no distinction between uppercase and lowercase in these. However, some implementations, for example, Dr. Rackett's teaching languages, require lowercase for reserved words and predefined functions. If a function has a fixed number of parameters such as square root, the number of parameters in the call must match all that number. If not, the interpreter will produce an error message. Section 15.5.4 Defining functions. A scheme program is a collection of function definitions. Consequently, knowing how to define these functions is a prerequisite to writing the simplest program. In scheme, a nameless function actually includes the word lambda and is called a lambda expression. For example, open parentheses, lambda, open parentheses, x, close parentheses, open parentheses, times x, space x, close parentheses, is a nameless function that returns the square of its given numeric parameter. This function can be applied in the same way that named functions are, by placing it in the beginning of a list contains the actual parameters. For example, the following expression yields 49. Open parentheses, lambda, open parentheses, x, close parentheses, open parentheses, times x, space x, close parentheses, 7, close parentheses. In this expression, x is called a bound variable within the lambda expression. During the evaluation of the expression, x is bound to 7. A bound variable never changes in the expression after being bound to an actual parameter. Value at the time evaluation of the lambda expression begins. Lambda expressions can have any number of parameters. For example, we could have the following: open parentheses lambda, open parentheses abc, x, close parentheses, open parentheses plus, open parentheses times axx, close parentheses, open parentheses, times bx, close parentheses, c, close parentheses. The scheme special form function defined serves two fundamental needs to scheme programming: to find a name given to value and to bind a name to a lambda expression. The form to define that binds a name to a value may make it appear that define can be used to create imperative language style variables. However, these name bindings create named values, not variables. Define is called a special form because it is interpreted by eval in a different way than the normal primitives like the arithmetic functions, as we shall soon see. The simplest form of define is one used to bind a name to the value of an expression. This form is open parentheses define symbol expression close parentheses. For example, open parentheses define pi 3.14159. Open parentheses define 2 pi open parentheses times 2 pi close parentheses, close parentheses. These two expressions have been tabbed to the scheme interpreter, and the pi is tabbed. The number 3.14159 will be displayed. When 2 pi is tabbed, 6.28318 will be displayed. In both cases, the displayed numbers may have more digits than are shown here. This form of define is analogous to a declaration of a name constant in an imperative language. For example, in Java, the equivalents of the above defined names are as follows. Final float pi equals to 3.14159, semicolon. Final float 2 pi equals to 2.10 times pi, semicolon. Names in scheme can consist of letters, digits, and special characters, except parentheses. They are the case sensitive and must not begin with a digit. The second use of the define function is to bind a lambda expression to a name. In this case, the lambda expression is abbreviated by removing the word lambda. To bind a name to a lambda expression, define takes two lists as parameters. The first parameter is the prototype of a function call with the function name followed by the formal parameters together in the list. The second list contains an expression to which the name is to be bound. The general form of such a define is actually general form of define and has its body a list containing a sequence of one more or more expressions. Although in most cases only one is included, we include only one for simplicity's sake. Open parentheses define open parentheses function name parameters close parentheses open parentheses expression close parentheses close parentheses. Of course, this form of define is the definition of a name function. The following example call to define binds the name square to a functional expression that takes one parameter. Open parentheses define open parentheses square number close parentheses open parentheses times number space number close parentheses close parentheses. After the interpreter evaluates this function, it can be used as in open parentheses square space 5 close parentheses, which displays 25. To illustrate the difference between primitive functions and the defined special form, consider the following. Colon. Open parentheses define space x space 10 close parentheses. If we define a primitive function, eval's first action is on this expression will be to evaluate the two parameters of define. If x were not already bound to a value, this would be an error. Furthermore, if x were already defined, it would also be an error, because this define would attempt to redefine x, which is illegal. Remember, x is the name of a value. It is not a variable of the imperative sense. Following is another example of a function. It computes the length of the hypotenuse, open parentheses, the longest side, close parentheses, of a right triangle, given the lengths of the two other sides. Open parentheses define space, open parentheses, hypotenuse, space, side 1, space, side 2, close parentheses, open parentheses, square root, open parentheses, plus, open parentheses, square, space, side 1, close parentheses, open parentheses, square, space, side 1, square, side 2, close parentheses, close parentheses, close parentheses, close parentheses. Notice that hypotenuse uses square, which was defined previously. 15.5.5 Output functions. Scheme includes a few simple output functions, but when used with the interactive interpreter, most output from scheme programs is the normal output from the interpreter, displaying the results of applying eval to top-level functions. Note that explicit input and output are not part of the pure functional programming model because input operations change the program state and output operations have side effects. Neither of these can be part of a pure functional language. Therefore, this chapter does not describe the explicit input or output functions of Scheme. 15.5.6 Numeric Predicate Functions. A predicate function is one that returns a Boolean value, some representation of either true or false. The Scheme includes collection of predicate functions for numeric data. Among them are the following. Function equals meaning equal. The not equal, then there is also greater than and less than. Taking consideration that not equal would be the less than and the greater than together. Then there is greater than or equal to, less than or equal to. Is it an even number, which is function is even with a question mark? Then there is odd question mark, and that means that is it an odd number or is it zero, which would be zero question mark. Notice that the names of all predefined predicate functions that have words for names end with question marks. In Scheme, the two Boolean values are hashtag T and hashtag F, or hashtag T and hashtag F lowercase. Although Scheme predefined predicate functions return the empty list, open parentheses, close parentheses for false. When a list is interpreted as a Boolean and any non-empty list evaluates to true. The empty list evaluates to false. This is similar to the interpretation of integers in C as Boolean values. 0 evaluates to false, any non-zero value evaluates to true. In the interest of readability, all of our example predicate functions in this chapter return hashtag uppercase F rather than open parentheses, close parentheses, period. The not function is used to invert the logic of a Boolean expression. I finished at 42 minutes in section 15.5.6, and the upcoming section will be 15.5.7. I will conclude this recording and I will post the second part soon. Thank you for listening.